This is the title of the talk, and in preparing this talk I was kind of aware that it's quite a mixed audience, and so I'm guessing, although it's not necessarily obvious who may be taking a long lunch and hasn't come back yet, but I'm guessing there's a mixture of people who actually have an interest in electromagnetic observations and then maybe ranging as far as people who just wondering kind of what the crazy things are that the EM observers keep telling them. And so I've tried to keep it quite general and broad. I am also aware that a lot of the science issues have already been touched on in other talks or are going to be covered in more detail in subsequent lectures. So in a sense I'm sticking fairly closely to the remit of just looking at observational techniques, constraints, difficulties, opportunities, challenges, all those kinds of things. I'm also going to depart, well I can move on actually, let's move on. Oh wait a minute, yeah, just to remind you, if you were wondering, apparently it is rocket science, even if it doesn't always seem like it. So the plan then is there, and so what I was about to say is I will sort of take some little detours in a couple of places to discuss particular science results which I think may not be being mentioned by other speakers, or at least certainly not in any great length, so I thought it was an opportunity just to kind of mix things up a little bit as well. And we will have an activity. I was shocked on the first day to see that Frank had thought up some activities for you to do, and even more shocked with balls flying around the room and all that. I don't have any balls, so to speak. But I do have an activity, and I will come on to that hopefully towards the end of this session. I guess I would like you to just be thinking amongst yourself, who are the natural born leaders? Who are going to be the next generation of PIs? Because I'm going to look for some PIs in due course. And so those of you that fancy the idea of being a PI may have the opportunity to do that. We shall see. Okay, so the plan of the talk then is, I'm going to start off, I thought, let's start off with gamma ray bursts. Why start off with gamma ray bursts? Mainly, I guess, because that's primarily my own background. So I've spent many years working on gamma ray bursts, so I'm interested in the science, I'm interested in the history, and I think it has some lessons for us moving forward, both from the point of view of techniques and observational challenges, and also from the point of view, of course, of the overlap of the science, and you've already heard a lot about that already this week. So we'll look at those lessons of history, then we'll think a little bit more about the gravitational wave, targets of interest, the electromagnetic emission mechanisms, and also remind ourselves why we care. I'll do that fairly briefly, and hopefully you'll already know why you care at some level. And then I'll try to set some of the scene in terms of observational constraints. And so we're going to cover, to a greater or lesser degree of detail, the whole electromagnetic spectrum. And there are some sort of observing constraints which are quite common, and which those of you that are already observers may find this childishly simple. Those of you that are perhaps of a more theoretical bent or coming very much from the GW angle may not necessarily appreciate some of these things, so I thought it was worth just giving you an introduction to some of those. Then I was also wondering to myself, how do you organise a set of lectures like this? And I couldn't really think of a better way of doing it in terms of covering, this range of electromagnetic techniques of interest than taking GW170817 as a sort of exemplar and kind of concentrating really on what actually happened in practice, why those things happen, and using those as examples really of the techniques that we are interested in. So we're going to do, the first part of that is searching for the counterpart, and then we're going to go hunting kilonovae. Then hopefully it'll be coffee break if this time is roughly right. Little diversion into a science result of interest to me, if nobody else. Some more on 1708-17, and then some considerations of the future, 03 and beyond. Okay, so let's start, as promised, then our history lesson for the history of gamma ray bursts. So many of you in this room would have been very small people, I'm sure, when these developments were taking place, if you were around at all. But taking you back nearly 30 years now, as of around about 1990, you'd say gamma ray bursts as a field was already a fairly mature field in the sense that the discovery had been, some 20 odd years before. But at that time, the progenitors and the origin and the distance scale of GRBs wasn't known, and so the predominant opinion in the wise and the good was that they were likely created by some events associated with galactic neutron stars, because of course the potential for very high energy and compact sources. And the first sort of nail in the coffin of that general hypothesis came about with the observation by the BATSI instrument on CGRO, which is shown there, which was able to obtain positions for a large number of gamma ray bursts, as you can see, nearly 3,000 over the course of about 10 years, and found them to have a very isotropic distribution on the sky. So this is contrary to what you'd expect if your galactic neutron star hypothesis had been right. You would have expected them to have been clustering here on the galactic plane, and they're not. Worth commenting at this stage, and we'll come back to this point later, that these dots here representing the GRB positions are probably, in most cases, in nearly all cases, actually rather smaller than the error region. So typically the positions that BATSI was giving you were not great. They were many degrees across, and so individually you couldn't tell where the gamma ray burst had come from, but collectively you could show that statistically it was isotropic, whatever the sources were. Okay. So things moved on. In 1997, this Beppo-Sachs satellite was launched, and that had the capability of not only detecting gamma ray bursts, but also obtaining X-ray images of the same region of the sky following the burst disappearance. So the burst is fast, but these X-ray afterglows were discovered to still be detectable by Beppo-Sachs many hours after the GRB had gone, and thanks to the power of focusing optics, which you have for the X-ray telescopes, you were able to obtain an image of the sky. You can see this is the fading afterglow here, and that was the first discovery of GRB afterglows, and it gives positions to, in this instance, a few odd minutes or so. That was good enough, of course, to then go off with optical telescopes and obtain the first optical afterglow observations. And so this one was obtained in February 97, and you can see that the source here had disappeared a week or so later. So this initial image was taken within 24 hours. This is all illustrating some of the issues that we're going to deal with later, right? So we're searching through large areas of sky, we're trying to identify our counterparts, and we've got to do it pretty quick and be quite well organised about it. Of course, at this stage we didn't know exactly what the challenge was, and so at some level it was, both luck and judgment combining together. But it's turned out to be the crucial breakthrough, because once you have an optical afterglow, you then have subarc second positions. You can place this event in its real astrophysical context, as we'll see. You can look for the host galaxy, and indeed a few months later the first spectrum was obtained of such an afterglow, and in that spectrum you could see these characteristic interstellar absorption lines. So this is gas within the host galaxy that's creating these very common, strong absorption features, so they're pretty much unmistakable, although as it happens there was an intervening system as well along the line of sight which also confused this spectrum a little bit, but the result was clear, and it showed indeed that GRBs, as you well know, are extragalactic. In this case it was a redshift of 0.84 and astonishingly powerful and luminous therefore. So there's now of course been sort of 20 further years of a great industry of following up these events. It remains a challenging occupation from just a practical point of view. Those of us who do it regularly, we get the messages through to our mobile phones typically at any hour of the day or night, 365 days of the year, and the idea is that you try and respond to those alerts. It is very much the same moving on into the gravitational wave era. There are even more GRB alerts at the moment than there are GW alerts, but that may change as we go on. And the product of making all the follow-up observations is it's too great for me to go into in any detail, but just by way of an example or a sort of list of the kinds of things that we can dig out from this follow-up. So of course we learn about progenitors, the systems which gave rise to the GRBs and potentially their evolutionary pathways, the explosion physics, the emission mechanisms, what actually gives rise to the light that we see, the spectra. You've already seen an example with all these absorption lines. If there was no gas between us and the GRB, then you'd get a spectrum which looked like that, a very pure continuum. The gas within the host galaxy is giving rise to these metal absorption lines here, from which you can get the chemical abundance within that galaxy, which is pretty interesting because it tells you about previous generations of stars and enrichment and what they have done to the gas within the galaxy. You can measure hydrogen in particular, and this turns out to be very interesting for other reasons, but save that for another day. You can measure gas through the intergalactic medium all the way along the line of sight, or for a substantial distance along the line of sight towards the gamma ray burst. And in this instance, it happens to be for a host galaxy which is too faint to be detected by HST. So we're able to obtain this detailed information even for extremely faint host galaxies. And with samples of GRBs, we can address these other issues, cosmological questions, population diversity, evolution over cosmic time. It's going to be some time before the gravitational wave the gravitational wave detections are sort of going out far enough to address cosmic time evolution, but nonetheless we can see a path forward there. Okay, what else have we learned? Well, in particular, the model for the emission from GRBs has become, one would say, certainly accepted, albeit not necessarily the case that it can match all of the observational data that we obtain in complete detail in terms of the simplest model. But that simple model tells us that something creates a very high power, high velocity jet in a cone of some size, not yet clear, as we'll see just how big the jet is. And within that outflow, some dissipation within the outflow itself due to most likely shells of material moving at different velocities, crashing together, creating shocks, leading to dissipation. That creates the initial flash of gamma rays, and that reflects the high time variability of the driving central engine here. And then the afterglow, which we've seen in the X-ray and the optical, that's created when this outflow impacts the ambient medium, and that is less variable. Both of these phenomena are non-thermal. They show a very broad spectral energy distribution, and from mapping that spectral energy distribution all the way from gamma rays and X-rays right down to radio, we can constrain the parameters of the model, we can test the model, and we can learn things about the jet and the ambient medium that it is ploughing into. So why do we think long-duration GRBs are jetted? In fact, short-duration GRBs as well, but most of the evidence we have comes from long-duration GRBs. And the reasons are not necessarily quite as solid as you might hope. So, you know, everyone says they're jetted, and assuredly they're jetted, but let's sort of review why we think these things. Well, we know jets are common in nature, so, you know, jets occur all over the place in astrophysics, and we don't have a full understanding of any jet in astrophysics, and so, you know, it's not unreasonable, at least, as a null hypothesis, that a system where you've got a rapidly rotating, collapsing core with accretion onto it could give rise to a jet of this sort. If we assume that there is a jet, the emission, of course, is only occurring over a much smaller range of angles, a much smaller solid angle, and therefore, oh sorry, I'm misreading my own slides. This is point 3. Therefore, because you're only emitting over a small solid angle, it reduces the overall energy requirement by, let's say, 2 or 3 orders of magnitude, and that is a significant relief, if you like, for the modelling, because otherwise you could be talking about energies which are, you know, of order of a solar rest mass or so, which is hard to achieve with isotropic models. But if you reduce that requirement by 2 or 3 orders of magnitude, it at least then becomes a more feasible proposition. If you know, as we now do, that GRBs are produced, long GRBs at least, by collapse of massive stars, then a jet helps you with the baryon loading problem, because if you get too many baryons in the way, and that doesn't have to be very many baryons, then it slows the whole thing down and you don't end up with this ultra-relativistic outflow. If the explosion is having to come out through the envelope of a massive star, inevitably there are a lot of baryons in the way. A jet, of course, can create a tunnel and, in principle, clear the baryons out of the way, and then you get an unrestricted view of the emerging jet as it comes out, and so that is also a satisfactory aspect. Finally, and I suppose this was is often cited as the key evidence, we see in some cases nice achromatic breaks in the light curve which look something like that, and that is well explained if GRBs are jetted, because we can imagine that at early times the outflow is moving at very high velocities. There's a very strong Doppler beaming, and so the radiation is emitted in a very narrow cone from each patch of the front of this ejector here. As you evolve with time, the outflow slows down, the beaming angle widens until eventually an observer can see a patch of this outflow, which is in fact wider than the outflow itself. So our observable region goes beyond the actual front of the jet here, and so at that time the flux density, if you like, declines more rapidly, and so you end up seeing a break in the power law light curve that's this characteristic feature. And so that should be, one expects, achromatic, and indeed in certain cases you see a beautiful example like that. In other cases it doesn't look so good, and so the actual interpretation of these jet breaks in individual cases can certainly be quite ambiguous, and I guess if I have a little message there, it's maybe take with a grain of salt any particular measurements of jet breaks, even ones where I'm an author of the paper in which they appear. You are permitted to take those with a grain of salt. Okay, so that's kind of mainly on long GRBs, which is not of interest to you, except in as much as there is some commonality of the physics. What we're more interested in, for the purposes of this topic, are the short GRBs, and so the realization that GRBs split into two populations was made very early as 1982, in fact. The evidence became much more compelling in the 1990s, and it is seen nicely on this famous plot where you plot the duration of the gamma ray flash against the spectral hardness of the emission, and you discover that if you put a dashed line down the middle at around about 2 seconds, it more or less divides this overall population into two sort of clumps, which are, of course, the long burst and the short burst. Now, you would immediately recognize there are some issues here. These distributions obviously overlap. They're not cleanly separated. This plot itself is detector dependent, and so if you make the same plot for a different detector, it will measure a different duration just due to the sensitivity of the detector and its energy passband. It's also the case, of course, that these are observed quantities, and what they translate to in the rest frame of the event depends on the redshift. And so, curiously, the separation actually gets less clear if you plot in rest frame properties. Part of this separation is due to the fact that the short bursts are typically at lower redshifts than the long bursts. There you go. So it's, again, if there's a lesson to take away from this, it is to be maybe a little cautious about what we necessarily mean about short and long bursts. Again, we can be confident there are two populations, but assigning any given event to one population or the other is not necessarily easy to do or can be done. And I guess there's going to be a sort of particular relevance we'll sort of think about a little bit more in terms of GW 170817 and GRB 170817A, and the extent to which that is a regulation short burst. Okay, right, well, so why do we think short GRBs have compact binary progenitors? We all do, I'm sure you all do. I don't really need to persuade you of that, but I'm going to go through some of the evidence that we built up even before the gravitational wave connection was observed. And so we've just seen a little animation there in the background. And what was the sort of key thinking? Well, initially, it's the fact that compact binary merger is, as the name implies, compact, and therefore it's easy to explain variability times of 100th or even 1,000th per second isn't a problem in terms of the size of the system. The binding energy is also very high, 10 to the 53, 10 to the 54 ergs, so in total there's certainly a sufficient energy reservoir to explain the 10 to the 50, 10 to the 51 sort of requirement that we think we see in terms of the radiation from short GRBs. So in that sense, at least, it's a hypothesis which is always attractive because it just ticked those boxes. Subsequent to that, once we started to build up samples of short GRBs with afterglows and therefore host galaxies, we could go out and look at the host galaxies and look at their properties. And one thing that became clear early on, and that was that the host galaxies of short bursts span a much greater range than the long bursts, in the sense that we have some short burst host galaxies which are of like this example here, an elliptical sort, where the amount of star formation happening in this galaxy has been very low for a long time, and the importance of that is just that it rules out makes very unlikely any association of short GRBs with massive star progenitors. So the long GRBs have massive star progenitors. Some people had speculated the short bursts might also have massive star progenitors. Those speculations were really killed off by this observation. So the fact that we see short bursts spanning apparently a large range in stellar population age is certainly consistent with neutron star compact binaries, because as we know, as you've seen, they have typically long merger times, or at least some of them have long merger times, hundreds of mega-years or giga-years. And so that allows you to then have a long time between the episode of star formation that created the neutron stars and the final merger. And that's illustrated here. I'm not going to go into detail, but showing the fact that you do have this fairly significant contribution of elliptical galaxies amongst the hosts. The other point, it's one of the figures that was on that last slide, but I'll show it again, is that we often enough find short GRBs apparently outside any obvious host galaxies. So this is an example where you look at this field and it's a very faint afterglow there of the short GRB. It's a little white dot inside the green circle. The green circle was the X-ray position. The optical image was a very nice Gemini image. And you can see on this image here, well, this is day 1 and this is day 2, showing it's fading away. But we can see these numbered galaxies here are just examples of nearby galaxies, all of which are plausible hosts, if you allow for the possibility of the binary that's created the short burst to have been kicked out of one of these galaxies. So we know that supernovae can give a substantial kick to the neutron stars. Again, that's already been discussed this week, and that in some cases can be a sufficient kick that it can throw the binary completely outside its host galaxy, and in the intervening giga-years, perhaps before it finally merges, it can get to some quite large distance. And that's my attempt at the PowerPoint animation. More of that as we go on. Okay, so.
Could you say the body of this kick? Like order of magnitude?
In terms of the distance that it reaches, or in terms of the velocity? Oh, well, I suppose, I mean, in terms of this particular case, I must admit, I mean, we've looked at all of these galaxies and we have redshifts, so we could kind of do that analysis, but I don't think we've worked the numbers out. But it will be, I would think, you know, a few hundred kilometers per second, kind of plausible numbers, I think, don't have a problem. In fact, if you give yourself a Hubble time to do it, then I think you could get away with an even lower value. Of course, you've got to climb out of the potential wells of the host galaxy as well, and that might, in some of these cases, be a non-trivial requirement. Okay, well, moving on, of course, the real smoking gun for the connection between short GRBs and compact binary mergers, I would say, since I was an originator of this work, came with this event 130603b. And so we can see our Hubble imaging here, where we looked in the optical and the infrared at roughly a week in the rest frame and then roughly a month, and saw a fading infrared bright point source, well, infrared bright by HST standards. And so that created a lot of interest, or one might say much ado, about a single data point. And so it would have been nice to have had multiple data points and more colours and all this sort of thing, but when you're sort of making an observation which is a kind of a bit of a stab in the dark, you're asking HST for a special allocation of time that wasn't given out in the original process, then you can't be too greedy, and so you ask for, you know, the minimum that you think you can get away with, more or less, and that's what we got. But it is a very interesting result for the following reasons. So what we could do was monitor the afterglow at early times, which is to say the first 2 or 3 days when we could still see the afterglow. We could do that in the optical, which is the blue points, the near infrared, which is the red points. I'm going to tell you a bit more about what these mean actually later in case people are not so clear about these distinctions, and then the X-ray and the black points. And what you normally expect is that the afterglows of GRBs don't change colour or very little, and so one would have expected the optical and the near-infrared in particular, which are not widely separated in wavelength, to track each other fairly well. What happened was that the observations we made with HST at 1 week showed only an upper limit on the optical flux and a detection in the infrared, fairly high confidence detection in the infrared, which showed the colour had changed. It had become markedly redder. And so if one then plots a model on top of here, which were the 2013 versions of the Barnes and Kaysen kilonova models, then it would suggest that you could explain that excess quite nicely with something like a 5% of a solar mass ejector kilonova. Now that finding generated a lot of interest, and certainly for several years I kept being told by theorists that this was too big a number and that it was hard to get this amount of mass out of a compact binary merger. We've now seen an example much closer to home where similar sort of values are now thought to be in play, and of course it's suggesting that there are other ejection mechanisms which are more efficient than we had perhaps anticipated, in particular the wind from the accretion disk. And so this certainly seems, I think, more plausible now, and indeed probably one should redo the numbers as well and see what the numbers are. There is, of course, one should say, a fairly substantial error bar here as well. So it's not an exact measurement. So with that in mind, people went away and also looked at some other old short GRBs and found one or two other examples where they thought there might be late time reddening, and indeed they found some. I mean, I think maybe in some respects slightly curious, because this isn't going so red, this is only in the sort of red end of the optical and quite late. So if you've got excesses happening in the optical at more than 10 days, then in fact that's more perplexing in many ways than our original observation. And so it's not crystal clear what exactly the explanation is in some of these old cases. We've been back and looked now with the benefit of 1708-17 and knowing the light curves from that event, we have been back and looked at essentially all of the interesting short GRBs to see what it tells us in terms of could they have been hiding an event like 1708-17 in the data that were required for them, or is it ruled out? And in fact you find a range. You find several in which the emission that you see is much brighter than the 1708-17 kilonova, and that's maybe no surprise at all, because of course we do expect the short GRB to have a bright afterglow, and so very often the afterglow will drown out any kilonova component, and so that's not telling you so much. In other cases though, that we had deep enough original observations that you ruled out, in fact, a kilonova as bright as 1708-17. So we already know, therefore, that there's a range of luminosity there. Again, unsurprising, but we're beginning to place constraints on it even before we have any further GW observations. And then there were also one or two cases which were consistent with the possibility of a 1708-17 event being there, detected in the light curve, but not having been previously identified, because basically distinguishing that from the afterglow with any degree of confidence is quite hard work. Okay, so we're pulling these threads together. So again, I made a little animation, pulling the threads together. We have our compact binary mergers. They may be detected as a short burst, for example, by Swift. They may, we now know, be detected as a gravitational wave event by LIGO. And the interesting thing, of course, is that we may also then, that tells us that we may also detect the kilonova event with optical and infrared telescopes such as the one there. Okay, so moving on then. Potential. So that's the lessons from looking at the short GRBs. What are the potential gravitational wave sources of interest? And so I've listed a bunch here, and of course we'd all love there to be a nearby core collapse supernova, but that wasn't in the title of the talk, so I'm not going to talk about that. Another possibility is neutron stars, let's say closer to home, that might have some kind of major reconfiguration of their mass, the sort of things that give rise to the giant flares on soft gamma ray repeaters, which are highly magnetized neutron stars. If you had such an event in a nearby example within the Milky Way, then that could be detectable from its gravitational wave signal. The ones we are going to concentrate on are these, of course, the neutron star binaries and neutron star black hole, although, like I say, I'm largely hanging this talk on what we did and learned for 1708-17, and so actually I'm not going to talk much at all specifically about neutron star black hole binaries. And then one might, of course, have spent some time thinking about black hole binaries, but again, I'm not going to. Of course, there was a good deal of excitement from the very first gravitational wave discovery, 1509-14, that happened to be coincident with an apparently just about significant Fermi GBM detection of a shortish GRB, perhaps. This is generally, I think, regarded as being, well, by some parts of the community as not significant enough to really call a detection, and by other parts of the community significant enough to call a detection, but not significant enough to actually claim a connection with the gravitational wave event for a variety of reasons. So, again, I wasn't planning to say much more about that, although if people want to raise that, welcome to. So that's what we're going to talk about. Now let's remind ourselves why we're interested in all this stuff. And so again, this is kind of rehashing things which you've heard at other times during the week, and I'm sure many of you are already well aware of all this, but let's do it anyway. And so the motivations we have for making these electromagnetic observations and doing this multi-messenger astronomy, of course, pretty big one is understanding the R process budget. So this is a very long-standing puzzle. Where do the heavy elements in the universe come from? This has been already discussed quite a lot, and so the fact that we are making significant progress in resolving this puzzle, I think, is of great interest. As has been emphasised, though, it's still a long way to go before we can really do, a careful accounting job here, right? So we need to understand much better what the yields are for individual events, how those map onto the population of binary mergers that give rise to those events, and then also, crucially, how that evolves through cosmic time. So it's no good just establishing what the production rate of our process elements is at redshift 0. We need to know or have some indication of how that's gone through the history of the universe in order to really see that it does or doesn't account for the bulk of the R process elements that we see have been produced. Okay, well, there's the Hubble constant and the cosmological parameters. I will devote a few slides to talking about this a bit more because later on, because I think that's not otherwise been discussed at the meeting, as far as I'm aware. From a GRB person's perspective, the fact that we are going to have the opportunity to look for the signatures of jets in systems for which we actually understand something about the progenitors is just a delight. So the fact that the gravitational waves are telling us about the compact binaries which have gone into making the jet and the observed properties of the jet, knowing something about the inclination angle, of course, is going to ultimately teach us a great deal about jet launching and behaviour. There is the astrophysical context, and so by that I mean we can place any events that we find in terms of the host galaxies and the immediate environment, and that can tell us something about the origins of the events, the stellar evolutionary pathways that gave rise to them, and again we've talked quite a lot about that already. It's a very rich and interesting area of astrophysics, and leading to a lot of important new results just at the moment. There's fundamental questions of fundamental physics. The most evident one, of course, was the one that was already highlighted, testing the speed of light versus the speed of gravity. The fact that there was only a 2-second or so delay between the merger event and the gamma rays being seen, at very least told us that they were both moving at c to pretty high levels of fidelity, and so otherwise they could have easily been hundreds or thousands of years, let's say, between these signals arriving. But the fact that it was only 2 seconds really places strong limits on any disagreement there. There's Bayes again. You already saw him, and so why am I showing you him? But basically, it's just to emphasize the point that, if nothing else, just from getting the position on the sky of the electromagnetic counterpart, we get improved gravitational wave parameters because we already know we can fix one of the uncertain things, the position, and so that allows you to do better with all the others that you're then trying to fit for. And then finally, well, again, we've already talked about earlier today the properties of the neutron stars, and in particular the neutron star equation of state, and how that can also be constrained from the electromagnetic features, the ways in which your observed kilonova depends on the properties of the neutron stars. Okay, right, well, now, you've seen simulations, right, of compact binary mergers which have taken thousands of hours on a supercomputer to produce. What you have here is a simulation of a compact binary merger that has taken thousands of hours of me fiddling around with PowerPoint to produce. I don't know if it's worth it, quite honestly, but once you get started with these things, it's like a challenge you can't put down, so that's the best I can do. And you can see that it produced a tidal ejector, and then there's a disk wind, and a jet, and all sorts of exciting things. So that brings me on to thinking about the emission components. What are we looking for? And again, all of these things have been spoken about, but I'll remind you what we might expect to see from a system like this. And so, yes, if it's a compact binary merger that produces an ultra-relativistic jet, then you could expect to see a short duration gamma ray burst. Now, I should say that before GW 170817, and some of you perhaps remember these discussions, a lot of people, myself included, said there was a very small chance of seeing simultaneous gamma rays with a compact binary merger within the LIGO horizon, because essentially of this beaming factor. So, because your jet is rather narrow and the beaming rather tight, it suggests that you would have to be lucky to be looking down the line of sight down this jet, so it wouldn't often happen. Well, of course, the first one that occurs, it does happen. It does happen even though we're not looking down the line of sight of the jet. Okay, more of that later. One of the things that the 170817 in particular sort of prompted was a development of these ideas which had been developed more for long GLBs, but the idea that if you already have some ejector coming out from your system, in this case the tidal ejector as the two neutron stars were getting closer together, then as the jet plows out through that material, it will shock a region, something we call a cocoon, around it, and that cocoon will be accelerated to higher velocity than the rest of the ejector. And that will have its own emission and dynamics, and so that is an extra component which has been invoked to explain some of the properties of 1708-17. Beyond that, of course, we have any emission from the various ejector components which have been discussed, the dynamical components and the wind components as illustrated there. Now, one might also comment that at some level this figure could be used as a sort of guide to how far away we could see this event. And so, you know, out here it goes a long way, if you like, or to the point it's bright, and so we could see, if we're looking at an on-axis jet, a long way away, but from elsewhere, although the emission is isotropic, so that's nice, but of course it's faint, and so we don't see it so far. Okay, right. What am I doing for time? Right, okay. I want to leave myself enough time to go hunting kilinovi. Well, we need to get into our mindset of how we go hunting then. So, what are the kind of issues that we have to deal with? We're interested in the first instance in finding the counterparts, and so we'll, for the moment, sort of assume that we haven't got any gamma ray information, so we'll just think about the information that comes from the gravitational waves. And so we've all seen these kinds of figures which show the localization region that you expect to get from 3 detector, at least, gravitational wave networks. And what we find in that case with just the LIGOs and the Virgo detector is that the size of the error region depends a lot on where the event happens on the sky. And so in some places the error region is still very large, in other places it's reasonably small, and we're lucky enough to get a reasonably small case for 1708-17. Of course, as we'll discuss briefly later on, with the addition of a 4th node to the network, particularly the one in India, then that could improve the overall location accuracy all over the sky. Now, these error regions, even these small ones, but certainly these big ones, are difficult for EM observers for the most part. So, for the most part, the fields of view of our instruments are not covering anything like these areas. So that raises one issue, which again will be a bit of a theme, which is, of course, we do know the location of galaxies in the local universe. So here is a map of galaxies out to about, I don't know, probably about a gigaparsec or so, maybe a bit less. With colour coding reflecting distances, and so you can see all the examples of clustering here. The Milky Way is cut out down the middle there, but there are lots of rich clusters of galaxies and filaments of galaxies in between those. And the fact that we know those locations and the distances at least reasonably well means that we can use them as potentially shortcuts to identifying the most likely locations and origins of any given gravitational wave event. And this we can sort of cut down some of the area potentially that we might have to search. And just to quantify that a bit, how much better that could make things, this was a curve produced actually for follow-up with a Swift satellite, but it's much the same argument if one is dealing with a smallish field of view optical telescope, for instance, where the two curves here show you for simulations how long does it take you to give yourself a better than 50-50 chance, let's say, of finding the counterpart. And so the answer in this simulation was, you can see the blue curve here, if we take the 50-50 line, you would get there within maybe a couple of hundred observations. This was looking at a very wide and large error region. Whereas if you'd have not made use of the fact you knew where galaxies were and deliberately targeted those, and you'd just tried to map the whole area, then you'd have had to map something in excess of 1,000 fields in order to give yourself a 50-50 chance of finding the counterpart. So that's certainly a useful thing to do, and you're even going to get a chance to do it later on. Okay, the other things you're going to have to think about, if you're going to be looking for a counterpart, you're going to have to think what waveband are you going to look in. And so this is the whole electromagnetic spectrum now, showing you which bands in the electromagnetic spectrum make it down to the Earth. And of course it's famously the optical and near infrared region here, and the radio. And other than that, everything's in space. So for the most part, we're interested in this region. And of course, life is more complicated than you first thought, because although you can sort of map out these regions, in reality, the gaps between the transmitting regions are slightly complex, and they vary a lot with altitude and conditions. And so you might, on one night, be able to observe in a particular wavelength, and then maybe in another night you can't, because basically there's too much moisture in the atmosphere. And so these things can restrict what you're able to do. I should say they also multiply up ridiculously the number of the amount of nomenclature we have in EM observing. And so we have a whole bunch of passbands with names in the optical and the infrared, and then another lot in the radio, etc., etc. So trying to make sense of any of that, unless you're actually really involved in it, of course, is a nightmare. Well, if we're interested in kilonovae, then we're probably interested in things which have black body temperatures, somewhere in the thousands of Kelvin range. So, of course, happily enough, that puts us in the kind of optical, near-infrared and near-UV region if we're wanting to find and characterize sources with those sorts of temperatures. And again, this is a plot. I'm just hoping this is of interest to you. If those of you that have never done any kind of observing, at least you'll see the sorts of things that we have to wrestle with. So what's on this plot here? What's on this plot? The white lines are showing us atmospheric transmission again in gory detail. So you can see here that there's high transmission just here and here, but then very low transmission windows in between. You can also see the purple lines there. The purple lines show you the sky brightness. So not only is the sky annoying because it blocks out certain wavelengths of radiation, it's also annoying because it is bright itself. And therefore, in certain regions of the spectrum, you get much brighter background sky than in others, and so that can reduce the depth that you can reach. And the colourful lines in between are the standard filters that we use. And so when we're making images in the near-infrared, we typically use those filters. We're making in the optical, then we have another range of filters. All of them have different numbers and letters and what have you. And in fact, this is a small sampling of all the possible filter systems that have been created over the years. And so I'm, again, just showing you this for those of you that are really new to this kind of thing, to sort of illustrate the technical complexity of it all. Okay, well, so you have decided maybe what you're going to observe and what waveband you're going to use. The other thing, particularly if you're observing in the optical and the infrared, is where is my target? And by that I don't just mean, where should I point my telescope, more of that later, but where is my target in particular relative to the sun? And in the case of 1708-17, it was not well placed relative to the sun. It turns out that, so this is a typical chart that we use for planning our observations, and basically it more or less shows you the night time in Chile, which is the place of interest, and so this is the beginning of the time that when you could observe, and this line here is showing you how high the target is above the horizon. So it was already below 40 degrees when it got dark in Chile, and then was dropping quickly. And basically most big telescopes are not going to observe much below about 25 or 30 degrees altitude. So we had this fairly small window of opportunity to actually make any observations of 1708-17. I should say, on the plus side, it was nowhere near the moon, which was only a problem towards the end of the night, and so that was a good thing. Next question you should all ask yourselves is, if you're going to plan, particularly if you're planning in the future, where making follow-up observations of gravitational wave events, is where are my telescopes? Where is the big glass? So there are telescopes, of course, dotted all over the world, but actually there are not, if we're talking about the largest telescopes, let's say the 8-meter class telescopes, then they are limited to essentially 4 geographical locations on the Earth. So ignoring this one here in South Africa, because that's a specialized spectroscopic telescope, and so it's not really able to make all of the observations you'd like. Basically, we're talking the Canary Islands, the Chilean Andes within a couple of hundred kilometers there of each other. The mainland US, again, fairly clustered around, and then Mauna Kea in Hawaii. And that's your lot. And so that is a pretty big issue. It's an issue because, if it's bad weather in, Hawaii, then that wipes out half of your big telescopes in the world in one go. And it's an issue, of course, from timing, because if, as we'll see later on, your event occurs when it's optimally placed for observation somewhere over the Indian Ocean, you've got to wait quite a long time before it's going to be observable with anything large and impressive. And I think more or less the last in terms of where the source might be and what could turn out to be bad news. Again, if this is news to some people, it probably isn't news to everybody, but the galactic location, if this is our Milky Way galaxy here, is of significance, because if we're looking out from our vantage point in the Milky Way at a relatively high galactic latitude, then we're happy, there's not much material in the way, we can see through what there is. If you're looking at a low galactic latitude, as illustrated there, then we're not so happy. Essentially, there's a lot of dust and gas along the line of sight, there's a lot of confusion as well, potentially many other sources in the way, and so all of that is not good. Right, well, 1708-17 turned out to be at a reasonably high galactic latitude, so that wasn't so much of a problem. It wasn't, though, well placed when it occurred. It was indeed in this scenario that I just mentioned. It was above the Indian Ocean, and therefore there wasn't a lot in the way of telescope acreage which could be pointed at it when it first happened, and that's why it took 10, 11, 12 hours before we found the counterpart. It wasn't just sort of laziness and, observational astronomers having a hard time getting out of bed. It was entirely due to the fact that we had to wait for the Earth to turn round before it would become visible at our telescopes. And this, of course, we benefited greatly from the fact that it was a three-detector detection or three-detector network which made the detection, and so that did at least manage to localize the region that we had to search in very well. And so this movie is going to sort of spin through what we found, and so I thought it was a good kind of summary. At the press conference when we talked about this, we were trying to compete with each other to see who could figure out the most appropriate piece of fruit or vegetable that you could hold at arm's length that would illustrate the size of the air region on the sky. I think something like a courgette was about it's a bit bigger than a banana, a bit smaller than a cucumber, so something of that sort. So the movie proceeds and we zoom in, and of course it's very easy, you know where to look now. There it is. It's going to change colour in a moment, I think. And so, life is very easy when you know where to look. Well, let's move on. So there were six ground-based observatories which made observations, if you like, before the announcement came from the first of those. So the first one that observed the counterpart was this one here. All of these other six made their observations before the announcement came from this one, so in that sense were regarded as independent discoveries. We carried on and made observations later and made detections later in X-rays and radio. And so let's just have a quick look at the kinds of things which you have to struggle with. So I've sort of implied to you the sorts of difficulties you have and maybe the strategies that you can make use of. And again, it's really illustrative just to look at the 1708-17 example here. And so the one that made the discovery, the famous Swope telescope discovery, it's only a 1 meter telescope. It's got an optical camera with a fairly small field of view. It's not an enormous field of view, 1/2 degree by 1/2 degree. But by virtue of the fact that this event was so relatively close by at only 40 megaparsecs, it meant that we were certainly within the possibility that it would be bright enough to be seen with a modest-sized telescope like this, and we were also well placed for making use of this galaxy targeting approach. And so you can see these examples of the Swope fields that it observed before it found the counterpart, and you can see how basically they were going about targeting those individual galaxies. Very similarly, in an even smaller telescope, only a 40 centimetre telescope, the DLT-40 telescope, made the next observation within a few minutes, and again following much the same kind of strategy, even smaller field of view,